Morning, everybody. Come on, everybody. Come on, everybody. Anybody have any questions on anything? Glad to hear it, Matthew. Got more people coming in. So I got a couple more problem types that I want to introduce you to in this chapter 6 material, and then we'll jump on to chapter 7. Plus, I'll introduce a little bit of general relativity, as that was what worked on it for my attempt at PhD. So I actually am ABD. I never completed my PhD. I did all the coursework and the comprehensives writtens, but I never did the never introduced my thesis topic, my dissertation topic, and I didn't finish, of course, my dissertation. But anyways, that was my field of love, which was general relativity. So I always take the chance to cover that as much as I can, and I think we'll be able to do that pretty easy today. I don't think I'll jump into chapter 7 yet, but either way, I'm going to do my best. So does anybody else have any questions? I know Patrick didn't, but if anybody else has any questions, now's a good time to get asked before we get started. All right, well, I'm going to go ahead and go then. One of my students made a recommendation about pins for me, so check this out. I'm going to turn on my document cam. And now I got pins with erasers, and they look like they got tattoos on them. Cool stuff, huh? So we got a bunch of boxes of different colors and all that good stuff. This is the first time I've actually written with it, so we'll see what happens. So we mentioned before, or at least hinted to you, that our weight that we feel on Earth, we've been using the equation weight is equal to mg. That's a very nice writing pen, but it's not very dark for you guys, is it? Maybe that's just because I just opened it. Yeah, that looks a little better on the second pass. So the weight, the formula we've been using is mg, where you put in your mass and multiply that by 9.8 meters per second. But we should now know that that's caused by gravity. So you can really write mg is equal to g times your mass times the mass of the Earth over. And since we're on the surface of the Earth, which doesn't vary hugely from the top of Mount Everest to the bottom of the Marianas Trench, we can just use the radius of the Earth squared. When you do that, you see the m's cancel out, and that gives you that g is equal to 6.67 times 10 to the negative 11th. We've worked out with these units before, so I'm going to leave that. We know that the mass is 5.98 times 10 to the 24th kilograms. And we know that the radius is 6.38, if I remember correctly, times 10 to the 6. And we square that. So when I do all that calculation, you can see, let's see, 6.67 e to the negative 11 times 5.98 e to the 24 divided by 6.38 e to the 6 squared, and I get 9.79908, and that's meters per second every second. We know we only use 3 sig figs, so really this should be rounded to 9.80 meters per second every second, and that's why we use 9.80. Okay, it's like I think somebody else came in. Me let those folks in. I heard a beep. Yep, I think Gavin, in fact, is the one that gave me the idea on the pen. So can y'all read that okay? I know it seems to be writing a little lighter because I use fine tip. I might should have got medium tip, but hopefully y'all can read that. So you might ask yourself, well, you know, how is it okay to use 9.8 when you see it clearly depends on the radius of the Earth, and the radius of the Earth differs at different places. For instance, you know that our Earth is an oblate spheroid, which means it's a little fatter at the equator and a little shorter at the poles, and that's because it's basically been more or less stretched by the tidal forces of the moon and the sun. So we've actually got a little bit larger radius at the equator than we do at the poles, but it turns out that's very, very small difference. And then you might think, well, what about at the top of Mount Everest? Clearly, that's much further from the center of the Earth than, say, sea level. And then what about at the bottom of the Marianas Trench or something like that? Clearly, that's much closer to the center of the Earth. Well, it turns out they are, in some sense, much closer, but the difference is really fairly minuscule. So I'm going to do that calculation now so you can see that it really isn't that that close to what we're talking about. So let's start off with calculating G for different locations. So what I know, for instance, is Mount Everest, the height of Mount Everest, which is the highest place on Earth, that used to be 29,035 feet, but we had a pretty major earthquake some time ago, and it's now 29,039, or excuse me, 32 feet, which I can translate into meters by calling it 8,848.95 meters, and that's only 5 sig figs. So 1, 2, 3, 4, 5 of these. So that's an extra digit there. So that's the elevation of Mount Everest. And remember, you're comparing that to 6,380,000. So here's 1,000, and here's 10,000, and here's the 8, and here's the 3, and here's the 6. So you can see that really this just lines up one digit beyond where we rounded our Earth radius to. So you can tell that's not that big a distance, but still we'll calculate it. And when we do, we get 6.67 times 10 to the negative 11th times 5.98 times 10 to the 24th over, now we're going to do 6,380,000 plus 8,848.95, and we're going to square that. And when we do, we actually get 9.7720 meters per second per second. And obviously that's only good to 3 sig figs, so we leave those off. So 9.77. It turns out if you want to do a percent difference or a percent error on that, delta G over G would be 0.03 over 9.80, which gives you 0.003 roughly, which means 0.3%. So if you use the normal radius of the Earth as opposed to the radius plus Mount Everest, you're only going to be off by 0.3%. So that's not a huge problem. The other end, the other extreme, is the Marianas Trench, which I thought that was in the Atlantic Ocean, but I know the deepest part of the ocean is in the Pacific now, and that may or may not be the Marianas Trench. I just didn't Google that to check, so you guys can check that out, or you might know off the top of your head because you're more worldly than me. So I'll say the Marianas Trench, which is really confusing since I got M up there, so I'll put an R in it. Marianas Trench, TR. Okay, that turns out to be 36,000, and I'll put H on it to mean, because I know I'm really meaning depth. It's 36,161 feet deep, which basically comes out to be 11,021.9 meters. Again, we got 5 sig figs, 1, 2, 3, 4, 5. So this is an extra one. When I do G for that, we're actually getting closer to the Earth, and since the R is on the bottom, that means R is getting smaller, or excuse me, R is getting larger. So we should actually get a actually getting closer. Excuse me. The R is getting smaller, so we should actually get a little bit bigger G. So let's look at that. We're going to do again 6.67 times 10 to the negative 11 5.98 times 10 to the 24 over 6,380,000 minus this time. So the denominator is getting smaller. That means the number itself should get larger, and that's minus 11,021.9. That is again going to be squared. And in this case, we get 9.8330 meters per second every second. Again, that's only 3 sig figs, but you can see again, it's about 0.3% difference from the normal number, the 9.8. So again, we don't, if we're actually touching the earth or touching the bottom of the sea or something, some part of the surface of the earth, then we're always pretty safe using G and don't have to account for the altitude. Unless you're looking for, precision to 0.1%. So anybody have any questions on that? All right. We've already shown you, and I want to make sure this is clear because I tried to look back at your notes and I think I might have misled you a little bit, but I want to remind you, if you want to talk about F12 is equal to the force, this is supposed to be, oh, look, it's my time. I get to use the, wrong thing. I get to use my eraser. And if I hadn't written in it like 4 layers before I erased it, it might have come off even easier. I'm tickled. Okay, so this is force on 1 due to 2. What we worked that out to be, or what we should have worked that out to be, I don't know if I made a mistake or not, it should be G times M1 times M2. Now, here's the kicker. We found a vector, since it's the force on M1, it should point from M1 to M2. And of course, that vector is, that points from M1 to M2 is R2 minus R1. Okay. And we will call that R21 because it's in the same order as the subtraction. This points from 1 toward 2. So that really is the direction. But it has the opposite order as the subscripts I used for the force. So that made it kind of ugly. Now, what you could do is you can still use that and just use that as a memory tool and say, okay, well, it's going to be over R21 times R21 hat. And then this would be squared. Because this process right here, and I want you guys to look at the best Newton video, Newton's gravity video that I put on your module in Canvas. There's one that's yours, and there's a better one, and then there's one that's called best. That's actually the best derivation of all these, I think, and that whole class went pretty well. I didn't make a bunch of stupid mistakes like I do when I go off script. So anyways, that works. This is perfectly okay. You just got to remember that R21 literally means you compute the vector R2 minus R1, and then you divide it by the magnitude of R2 minus R1. And when you do that, notice what happens. It's not only does it become 1 long, but it doesn't even become 1 meter long. It becomes 1 unit long. So it doesn't screw up this formula and give it the wrong units, nor does it screw up the formula and give it the wrong size. Now, as you can tell, this R21 is really the vector R2 minus R1 or this R21 hat, excuse me. I don't know why I didn't write a hat there. This R21 hat is defined that way. And if you notice, this right here is the same thing as this R21. So you can also write this as F12 is equal to G M1 M2 over R21 cubed times R21. That works just fine. Okay. Notice by putting a third one down here, I'm doing the computation of making R21 myself. So I'll put a regular vector symbol on this one instead of a hat. Now, if you don't like the fact that the actual subscripts are in the opposite order, then you can also do this. You can say it's negative G M1 M2 over R12 cubed R12. So by putting that negative, you actually flipped it, and you can use the 1, 2, and everything matches. So all of these are actually valid expressions, and they all work quite nicely. So I recommend you finding the one you like, and try implementing it a couple times just so you can get used to it, because it's really easy. You really just have to compute a vector that points from the origin to the mass 1 and a vector that points from the origin to mass 2. And the way you do that is you do coordinates. So if you look at that best video, one of the things I did in there was I computed a vector from data points. So for instance, we could have had that problem we did the other day, which was basically this. I'll do it in black so you see it. I'm going to have, this time I'm going to make the XY coordinate systems different than I did on Monday. I'm going to say this is my X, this is my Y. I'm going to have M1 at the origin. And remember, that was the 0.16 times 10 to the 9th kilograms. And then I have M2, which is also 0.16 times 10 to the 9th kilograms. This one was at the origin, and this one will be at 100 meters, 0. And then we'll have M3, because it's supposed to be an equilateral triangle. We'll have M3 up here, and M3 was 1.0 times 10 to the 3rd kilograms, but its coordinate would be 50.0 meters. And then we did basically, this is 100 meters, and we needed 100 meters times the cosine of 30 to get this, and the cosine of 30 is 0.866, so it's 86.6 meters there. Okay. So when you have this, we've already worked this problem out, but now you can work it with this formula if you want to. The first thing you do is write R1. And the way you'd write R1, check this out. I'm just going to take, I need a vector that points from the origin to the mass 1. Well, what that means is my final point is where it's at, and my initial point is where it started. So I'm going to go, final point is 0, but the initial is also 0, and that's the X component. So I'll put I hat in front of it. And then final point is again 0, as I see right here. And I'm going to subtract the initial point, which was the origin. So that's 0 as well. So that's J hat. So that's R1 automatically. That's really easy peasy, right? R2 is actually quite easy. But again, I'm going to do it. All I have to do really is I take 100 meters, 0 minus 0, 0. And when I do the X minus X, that's 100 meters minus 0, I get 100 meters I hat. And when I do 0 minus 0, I get 0 meters J hat, which I can just write as 0 J hat. Okay. And then finally a vector R3. In that case, I do final minus initial as always. So really what I'm doing is I'm taking 50.0 meters minus 0 meters. And I'm putting that in front of the I hat. So literally, I'm just taking the coordinate, the final coordinate, which was 50 for the X, minus the initial, which was 0 for the X. And then I take the final coordinate, which is 86.6, minus the initial coordinate, 0 meters for that one, for the Y. So I get 86.6 meters minus 0 meters J hat. So that's really all you have to do to find a vector. Is like if you wanted a vector from, let's say, the point vector from let's say 1, 1, 0. So that would be, basically right here where this is, say, well, let's say 1 would be here and 1 would be here. So it'd be right there. If I wanted a vector there, pointing from there to, let's say, 2, 5, 4, then all I really have to do is I can say that vector would be, and let's call this A, and let's call this B. Vector A to B is just going to be, I'll do 1 minus 2, 1 minus, or excuse me, I'm supposed to do 2 minus 1. Sorry about that. It's always final minus initial. Let's don't forget that. That's the main point, final minus initial, just like our deltas have been. So I'm going to say it's from A to B. So it should be 2 minus 1, and then 5 minus 1, and then 4 minus 0. And by putting that little bracket on it instead of the parentheses I normally do, then that's another nomenclature that we can, or another symbology we can use to represent vectors. So I can say this is 2 minus 1, that's 1, 5 minus 1, that's 4, 4. And that's the same thing as I hat plus 4 J hat plus 4 K hat. Okay, so that's really how you have to do the vectors now. You always just take the final coordinate minus initial coordinate and make the coordinate subtraction problem into a component from which it came. So if it came from the X, then that's the X component. If it came from the Y, then that's the Y component. Any questions on that? All right, so that should be fairly straightforward. Some other things we want to do is we want to consider how your weight changes, say, from being on the North Pole versus being on the equator. Okay, so let's look at that problem. And then I want to do an orbital problem. And I think at that point, I've given you enough examples to make sense of this entire chapter. You can do other things, of course, as well. But the main thing is, let's imagine we have a planet Earth that has a radius r with a plus sign and a circle. Okay. We have a person standing on top of the planet at the North Pole, and a person in Ecuador, say, standing on the equator. And I want to find basically how much they weigh. So for Ecuador, we basically have a person standing on a scale like that. I'm going to call that direction the positive X direction. And I'm going to say the person has a mass M. This one also has a mass M. Okay. Now my forces acting are the force of gravity, which is obviously acting in the negative direction. So I'll give that the red vector. And that is really the mg, if you will. And then the other force I have acting is in the positive direction. And that's the F for the scale, which I'll just call F sub S. Okay. But what we know is the person must be, in fact, rotating or accelerating towards the center of the Earth to stay on the Earth. So we know the acceleration is AC. Okay. So when we go to write Newton's second law of motion, we're going to say the summation of the forces in the X direction equals mass times acceleration in the X direction. So what I have is F scale minus mg is equal to m times v squared over r. And we know the r is that. And the v, of course, v is 2 pi times the radius of the Earth. As we're assuming the radius of the Earth is right here, and it's going to go around a complete circle every day. So that's 1 day times, of course, we need to convert that to seconds. We know that 1 day is equal to 24 hours. And we know that 1 hour is equal to 3,600 seconds. So that's what our speed's going to be at the equator. I can compute that real quick because it's interesting to know. And in fact, obviously it changes. It goes down as you go higher and higher latitudes, because remember, latitude is just the angle up from the equator towards the North Pole, or down from the equator towards the South Pole, if we're talking about south latitude. So when I do this, I'll say 2 times 3.14159. My calculator's a pain in the butt to get to the actual pi, so I usually just type it in. Times 6.38 e to the 6 meters. And now I'm going to divide this, and we use parentheses. I'm going to say 1 times 24 times 3,600, which y'all probably recognize that is, I think it's 86,400. And that's 2 pi r over t. And that gives me 463 meters per second, or 463.96 meters per second. I only use 3 sig figs on the r. So I really shouldn't be carrying those. So I really should be calling it 464, but I'll carry the extra digits just to make subsequent calculations better. So that's what my acceleration is, or excuse me, that's what my velocity is. So now I can calculate the right-hand side. That means Fs, which is what your scale is going to read, is equal to mg plus mv squared over r, which you can write as m times g plus, we now have 463.96 meters per second squared over 6.38 times 10 to the 6th meters. That look more like a 6. Okay. So we can add all this in. That's just 9.8. I'm going to do that calculation so I can find out what the acceleration is. So I'm going to take and square that, 463.96, and then I'm going to divide it by 5.38 e to the, or excuse me, 6.38 e to the 6th. And that's going to give me 33.74 times 10 to the negative third.
What is the radius again? Is that an 8.9 or something?
6.38 times 10 to the 6th. And this
okay.
463.96 was the other one, sorry. Okay, so what I can see now is I'm going to obviously take this number, which is 10 to the negative third. So really what's happening is if I move this to the appropriate decimal place, I have to move it 3 places to the left. So it's going to be 0.033 being added to 9.8. So I can say plus 9.8. And that gives me that my weight is not going to be mg. It's going to be m times 9.83. And since I really should have 3 sig figs, I could really go that far if I wanted, but it doesn't really match any further than that, 374. But since the 9.8 was only known to 2 decimal places, we only know it here, and that's meters per second per second. So it's as if gravity really is a bit larger. In fact, it's comparable to the change of going to the middle of the or the bottom of the St. Marianas Trench, because it got about 9.83. Okay. Did I do something? Let me double check that. That's plus Fs minus mg. Mg should be yeah, that's why. Anybody notice any problems about my acceleration and my signs or anything? This is a good time for y'all to catch something. Well, it's also the time that Mr. Younger screwed up again. What direction is my acceleration according to my free body diagram?
Negative.
Yes, it's going that way. I did not force myself to put a negative there, and that screwed everything up. When you're on the equator, your weight should actually be decreased, because part of your weight's just going to keep you accelerated towards the center of the earth. When I got a 9.83, I knew that was wrong. Okay. So what was supposed to happen was we were supposed to say actual calculation, we're supposed to say F sub S minus mg is equal to minus mv squared over r, like that, which would have given us F sub S is equal to, when I pull this over here, it's going to be mg minus mv squared over r, not plus. So I left off that sign. That sign should have been a minus here. And instead of adding, I should have gotten 9.77 roughly. In other words, 9.8 minus 0.03374. So that's really what should have been there, not this number. Okay, so now I can correct it and just say m times 9.7662. So that's what the sort of what gravity feels like at the equator. So the answer at the equator, or at Ecuador, is that your F of the scale, dummy. F of the scale is really m times 9.77 to the appropriate number of sig figs, meters per second every second. So yeah, at the equator, due to the rotation of the Earth, part of your weight is just doing the work that gravity now doesn't have to do. Gravity's got to pull on you strong enough to make you have an acceleration equal to v squared over r. And since the weight is actually acting that way, that weight or that gravitational force is helping that, so it reduces the load on the scale by an amount equal to mv squared over r. And in fact, you get that. So everybody note that this was supposed to be minus and this was supposed to be minus. Blue minuses are corrected. Calculations. And again, we have yet another day where Mr. Younger's made another series of mistakes. And it's terrible because I usually do them before class. This one I didn't do because I've done it 1,000 times, and you can see I unintentionally went off script. Now, the other part was, what about at the North Pole? So at the North Pole, what we have is an object of mass m having f scale. I'm going to call this the x-axis. It's going to have f scale acting upward, And since that's the positive direction, I'm going to make F scale a blue or green force. I did blue this time. Okay. And then I'm going to have the weight, which is mg, being a negative force. And notice, since the Earth is rotating under me like this, I'm not accelerating at all. So in this case, you get the summation of the forces is equal to no acceleration. So you get the summation forces in the x direction equals mass times acceleration in the x direction, but that's 0. So you get Fs is just equal to mg, which is m times 9.80 meters per second per second. So everybody see the difference in those two scenarios? Does that make sense to everyone?
Yeah.
All right. Thank you for replying. So that's a pretty neat little scenario. Of course, when you do it right, it's neater. But yeah, hopefully y'all expected your apparent weight to decrease over there on the equator and to remain the same at the North Pole. But if you didn't, that's okay. That's a typical normal thing. Okay, that's one of the new physics concepts that you're supposed to learn from your first physics course, or if you've had another course, you probably should have known it already, but that's okay if you didn't, because now you do. All right, so let's do another one. Let's do a geosynchronous orbit. Let's actually figure out the equilibrium situation for a geosynchronous orbit. So I want to know what are the altitude and velocity of a satellite. I hate this word. I feel like it should be like 42 T's in here. And I never remember whether it's 2 or 1. So I'll just do that and write that and then realize I don't have spell check. Satellite. And I'm pretty sure, is it 2 T's and then an L, or is it 1 T and 2 L's, or anyways, y'all know what I'm trying to say. So what is the altitude and velocity of a satellite in geosynchronous orbit? So geosynchronous orbit is an orbit that you put it in space and it moves at the exact same rate that the Earth rotates, so that it's always over the same spot on Earth. And for instance, has anybody ever heard of any satellites being in that type of location? Or can you think of an example where a satellite might be in a geosynchronous orbit? From your life, maybe?
Oh yeah, like satellite TV and GPS, I think, right?
Yeah, exactly. Satellite TV and GPS is another one. Satellite was what I was thinking of, satellite TV. The reason why, for instance, you'll see a commercial for what's that internet company? It's not Fios, but there's an internet company. This pretty black-haired girl wearing a gray sweatshirt or hoodie or something walks up and saying, "Yeah, you can get great internet, blah blah blah," and it says something like, "As long as you've got a view of the northwest sky," or something like that. What that tells you is you need to have a view of a particular spot in space in a particular direction, at least. She didn't tell you how far. So if she says in the northwest, you might say, okay, well, it must be, I got to look this way. Well, what that would suggest is probably the object's in a geosynchronous orbit above somewhere northwest of you. So that's really what the geosynchronous orbit is for. That keeps us from having to have a satellite dish that constantly moves to track the satellite, right? You just put your satellite up, dude aims it till it gets the best signal, and then tightens it down and you're done. So yeah, that's what a geosynchronous orbit is. And what it looks like is basically just an object at some distance away that rotates, or I should say revolves, at the same rate the Earth rotates. So first off, I want to calculate the velocity, sort of, but I also want to calculate the distance away, because the distance away dictates what the velocity will be. So really what's happening is I have an object that is subject to forces. Okay, the object is going to be a satellite. It has a mass m, and I'm going to imagine that it's directly above, Kansas or something right now. Okay, the forces acting on it are going to be what I call the positive x direction. They're going to be in the positive x direction, and it's going to be the force of gravity. Okay, so gravitational attraction will be pulling it this direction. Actually, I like using green instead of blue for my positive because it's like a green light. So that force, though you could call it mg, we're now talking about heights that are probably comparable to r. So you don't necessarily want to use mg there. In fact, you want to use g m of the Earth over r squared. And this r in here, by the way, is r of the Earth. So I should put right here that circle sign. Okay, so this r is going to be a bigger one. It's going to be from here to here. Okay, so that's got to be the force on it. And we also know that it has to accelerate in this direction with a centripetal. Okay, so a centripetal is equal to v squared over r as well, again with the same r there. So believe it or not, that's really all the forces that are acting. People always think, oh, you've got to add a centripetal force. No, you don't do that. Okay, the centripetal, this v squared over r is not supposed to be on the left-hand side of Newton's second law. It's supposed to be on the right-hand side because it is an acceleration. Okay, so when I write the summation of forces in this x direction is equal to mass times acceleration in this x direction. Notice I did choose the acceleration direction to be positive, unlike the one I did up there, which is what screwed me up. I did do it correctly this time. So now I'm going to say g m times the mass of the Earth divided by r squared has got to equal m, the mass of the satellite, times v squared over that same r. And in fact, you can now say, all right, well, I can get rid of one of these r's like this. Okay, so now I have, and also I can get rid of the m like that. So now I have gm Earth over r is just equal to v squared. But luckily, v squared can be found because v is equal to 2 pi times that same r over the period. So I can eliminate eliminate v and get it all in terms of r and t, but I know what t is. T is the time required for it to go here to here, which most of you would say is roughly 24 hours, right? And that's sort of right. Actually, the 24-hour period is a little bit longer than that. Actually, the Earth makes a rotation in 23 hours, 56 minutes, to be honest with you. But we'll just round it to 24 hours. Okay. So T is equal to 24 hours. And then, of course, 1 hour is equal to 3,600 seconds. And when you do that, you'll get that number I mentioned earlier that I figured you all knew, 24 times 3,600, and that's the 86,400 seconds. Okay. So now I can plug this in here and I can say g m of the Earth over r is equal to 4 pi squared r squared over t squared. Okay. So now I've got r cubed and everything else I know. So I can say r is going to equal g m star, or plus I should say, over 4 pi squared, and then times, of course, t squared. So I can put all these numbers in, 6.67 times 10 to the, this is R cubed, by the way, times 10 to the negative 11th. That's newtons meters squared per kilogram squared, times the mass of the Earth, which is 5.98 times 10 to the 24th kilograms, times 86,400 seconds squared over 4 times pi squared. And make sure I didn't move off anything. The R comes over there. I got 4 pi squared, T squared all over there. Yeah, that all looks good to me. Does anybody see any mistakes I might have made? I don't either. So 6.67 e to the negative 11 times 5.98 e to the 24 times 86,400. And now I'm going to divide that by parentheses 4 times, now's a good time to use the pi function. And I get 872.93 times 10 to the 15th. And I think you can tell that this kilogram canceling out with that gives a Newton meter squared per kilogram. And then Newton is a kilogram meter per second squared. So this second squared cancels out with that second down there. So I get a kilogram meter per second over a kilogram, excuse me, a kilogram meter per second over the remaining kilogram. So that just gives me that kilogram canceling out. The seconds already canceled out, and that just leaves me meters times meters squared, which gives me meters cubed. So I can now say that R is the cube root of that value. So I'm going to raise it to the parentheses 1/3 power. And that gives me R is equal to 955.7 times 10 to the 3rd meters. That's 10 to the 4th, 10 to the 5th. That's really pretty small. That's a close orbit, in other words. Let's make sure all our numbers work out. I did do 6.67 times 10 to the negative 11th. I did 5.98 times 10 to the 4th. I did 86,400. All that looks right to you guys, right?
Yeah, that's good.
Okay. I'm getting way off on my numbers. Did I type in a 24? I did type in a 24. Oh, I didn't square my 8,600. My 86,400. Yeah, I just wrote that once. So yeah, that make a big difference. All right, so let's see what happened. So R is really going to be equal to the cube root of, let's see what I get when I multiply this by 8,600 like I was supposed to. $86,400. That gives me 75.42. 1 meters cubed. So I worked really hard to get the units right, and I did do that luckily. But this being 10 to the 15th was not nearly good enough. The 10 to the 21 is more like what I need. When I was coming up with this number, that was putting me more or less within the surface of the Earth. So that's why I knew I got it wrong. And luckily that was able to point me to this. So when I take the cube root of this number, I can raise it to the 1/3 power, in other words, and then I get 42.25 times 10 to the 6 meters. 74.21 times 10 to the 21.
I've got a question, sir.
Yes.
Why is this whole equation equal to r squared?
It should be r cubed.
Oh, is that a cube?
Yeah, that's the exponent of 3 here.
Okay, yeah, difficult to see.
Yeah, well, yeah, good for you to watch though. That's exactly the kind of thing that I'd screw up on. And let me make sure r cubed was the right one. So, yeah,
It seems like it, yeah.
Yeah, the r cubed comes up here. The t squared would be in the bottom. God dang it.
So
Anybody see any problems with this algebra right here? That looks right to me. I've got an r cubed is what I'm solving for. That would be a g, an m, and a t squared on top, and a 4 pi squared on the bottom. So that all looks good. Yeah, this
what
is,
did
matches
you
what the
came
book
out
had
to?
too. Go ahead.
Oh, never mind. Okay. What was confusing me is you wrote 42 times 10 to the 6. I got 4.2 times 10 to the 7.
Yeah, my calculator has a scientific or engineering notation, and it automatically rounds it to a power of 10 as the a power of 3. It's like 3, 6, 9, 12, those sort of things. So it always does those, which is kind of nice. But yeah, it'll throw you for a loop, and that's what threw me for a loop too, because I expected to get 10 to the 7th, but then I realized, duh, it's 42 times.
Yeah.
So, okay, so that's our geosynchronous height, and that's actually from the center of the Earth. So that's not really the altitude, and I did ask for the altitude. So we now need to take that, which is altitude would be 42. That's basically 42 million. So 42,250,000 meters minus, now we're going to write the radius of the Earth, which is 6,380,000 meters. So I think you can see that that's basically going to get 0 minus 0. This will be 13 minus 8, which would be 5. And this would be 11 minus 3, which would be 11 minus 3 would be 8. And then 11 minus 6 would be 5. And then 3, like that. So it should be about 3 million feet up, maybe. Let me not do that by hand just to be safe. So I'm going to say minus 6.38 e to the 6. And that gives me, about 35 million, or that actually gives me 35 million. So the altitude for geo is going to be about 35.87 times 10 to the 6 meters. So it is in fact comparable, but even bigger than the Earth's radius by about a factor of 10. Okay, you can also calculate that speed now if you wanted. So we could do the 2 pi r over t, and when I do that, I'm going to say 2 times 3.14159 times 6.38. Oh, no, not 6.38. it's R, which is 35.87, excuse me, which is 42.25. So that's my 2 pi R. Notice what I wrote there. I've got the 2 times pi times that distance, which is really my distance from the center of the Earth. And now I'm going to divide that by 86,400 seconds. And that gives me basically 3,072 meters per second. And that's carrying 1 extra digit. So now you know what the geosynchronous orbit parameters are, and you can solve, other problems like this. They could ask you, how fast would the satellite have to go if it crossed, if it was going twice as fast as the Earth, for instance, and then in which case it wouldn't take 86,400 seconds. It'd take 43,200 seconds. So that's another type problem you could solve, and that's really about it. There's not much left to this. There's simple problems of you can use the Kepler's third law to solve for the period of an orbit. And in fact, the niceness about Kepler's third law, we derived Kepler's third law and got that it was like t squared is equal to 4 pi squared over g times the mass of the sun times the semi-major axis cubed. Well, if you use meters and seconds and all that stuff, yeah, you got to put all this crap in. But guess what? If you use this in years and you use this in astronomical units, what would this constant become? All you need to do is think about one planet's value. Yeah, it's time to go. You guys can split. I'm sorry, I didn't realize how late it was. You're welcome to go, but I just want y'all to think about that. This number just becomes 1 because for Earth, the period is 1 year, and for the sun, the astronomical unit is 1 year. So this must be 1. So just keep that in mind. That's another neat little trick that'll make your life a little easier when you go to solve problems. Other than that, you're free to go. We're going to start chapter 7 next time. Have a nice one, and I will see you guys Friday or at lab.
Thank you, Professor.
You're welcome. Thank you for coming. Chapter 7 we haven't covered. Chapter 36 we haven't covered, so that doesn't matter. Remember, it's those dates don't matter till we start covering them. So next time I'll cover chapter 7 or start covering chapter 7, and I'll fix that date then.
What was the speed that you came out with again?
3,072 meters per second. Actually, your book does a similar example, and they got 3,070. So yeah, that's that's even exactly correct to my number of sig figs. So
what was it? You said 3,070?
3,072. Yeah.
72. Gotcha.
Yeah, if y'all can see enough to or type quick enough when I say the words, do try to back up my calculations so y'all can see from me making some stupid mistake like this one. I mean, they're still my mistakes. I don't mean that y'all are the problem. It's me, of course, but I just want to make sure you guys are doing that so you can get the feel for how to calculate this stuff. Anybody else have any questions? Mary, Brandon, Tyler? Tyler's got the empty chair going.
Yeah, I wonder what happened with him. Ever since I came into the meeting, he's had an empty chair.
Yeah, I think he normally watches like a child or sibling or something like that. So
maybe
work at the house. Us grown-ups having to do stuff.
Yeah. All right, thank you.
All right, see you, Gavin. Brandon, Mary, Vincent, do y'all have any questions? All right, well, I'm going to end the meeting. Y'all have a good one.